All right, Brandon Clayton here, the Algebra Guy. Today, as you see on your screen, we will be solving quadratic equations using the square root property. So there's many ways to solve a quadratic equation. Here's one of the more popular ways that you could do so. So what do we want to cover by the end of this video? We're still in lesson or TEK 8A, solve quadratic equations, having real solutions by taking the square root. As you can see, we've done factoring already. We haven't done these others, but we're going to be focusing on the square root property today. And as you see this form, we'll come up again, solve quadratic equations of the form ax squared equals k, where k is some number using the square root property. A parentheses x minus h squared, we're going to put them in that form too. I'm going to show you how we can isolate this x when it's in this situation. So we've already talked about how we can solve this equation, x squared equals 9. And it's pretty simple in your head, right? But if it wasn't so simple, we still have talked about a way. And one of the ways we talked about is using the difference of perfect squares, where we're going to subtract 9, and therefore we get x squared minus 9 equals 0. And we realize these are the difference of perfect squares, and we can break them into two factors, x minus 3 and x plus 3. And once we do that, to get 0, we can just simply put in or solve this for for x, and we get 3 and negative 3, because x minus 3 equals 0, that'll get 3. X plus 3 set equal to 0 will give you a negative 3. So we get two answers, plus or minus 3. So that's one way we talked about. However, what would you do if you have x squared equals 7? Because x squared equals 7 doesn't work out so friendly, because the square root of 7 doesn't give us some kind of whole number like this friendly 9 just did. So if we did the square root of 7 and we subtracted it both on 7 on both sides, we end up with this. And we don't have a perfect square here that we can simply say, oh, let's just put that in x minus 3 and x plus 3. We can't do that anymore. So how would you do this? I want to talk about how we can handle situations like that, because you will get those situations. So here's the rule. If x squared is equal to k, some x squared is equal to k being some real number, and k is greater than or equal to 0, then x is going to be equal to the square root of k. So this is simply saying, if you have this situation, know that your x is going to be equal to whatever the square root of k is, or x is equal to the negative square root of k. So it can be the positive or the negative square root of k. So we'll look at what that looks like here in just a second. And the point here in this sentence is just to notice that you do get two solutions, a plus and a minus, just like we did with the plus 3 and the minus 3 a second ago with the x squared minus 9. So let's try this same problem again, but this time using the square root property. So instead of subtracting 9, I'm going to simply take the square root of both sides. So before I really delve into this, because we're going to do this quite a bit in this video, understand that by taking the square root is undoing this squared. So we talk a lot of times about if I had, for instance, 3x times 12. How would I find out x? Well, you would do the opposite of multiplication, because 3 is being multiplied by x, so I would do division, right? So we'll do division. That gives me x equals 4. But what if I had something that was squared? How do I undo that? Well, now you know. You can use the square root to get rid of that squared. So that's how I want you to think about this square root and square relationship. So by taking the square root of this side and the square root of this side, this now gives me x on this side, but it gives me two solutions over here, plus or minus the square root of 9. Now I'm going to talk about why it gives us two solutions here in this next step. Because we see that square root of 9 is 3, and we still have this plus or minus here. But why plus or minus? Because we discovered recently, right, that we have a positive 3 and a negative 3 as answer choices. So we know those two are answer choices. However, practically it makes sense, because if we were to put 3 back into our equation, our original equation, it'll give us 9. 3 times 3 squared will give us 9. 3 squared is equal to 9. But that's not the only thing that will equal 9. We also know that negative 3 when you square it will equal 9. So those two solutions need to be represented. And we'll try to remember. Sometimes I forget. So remind me if I forget. Just yell out to me, hey, Brandon, you can't do that. But it's going to be plus or minus every single time we take the square root of something, because you can square that number to get back to your original problem. So those are our two solutions, 3 and -3. But what about this 7 situation we talked about a second ago? How would we have handled that? Well, let's look down here and see. X squared equals 7. So this time, instead of trying to subtract 7 and do perfect squares, because it's not, we're going to do the same thing and take the square root on both sides. And that gives us x. And the square root of 7 gives us square root of 7 plus or minus. But we can't simplify square root of 7 to anything. There's no perfect squares that can be simplified, nor does it give us a whole number. So we leave it just the way it is. And I would repeat, in algebra, for the most part, fractions are your friends, as opposed to earlier grades when you prefer decimals. And in this case, radicals are, because radicals represent a much longer decimal, and by simply saying square root of 7 will save us a lot of headache. So square root of 7 and negative square root of 7 will be both our solutions. So leaving it that way, and then sometimes students have a problem leaving it this way because they want a decimal because it doesn't seem like a real answer, but this is a real number. Square root of 7 and negative square root of 7 are perfectly fine. Matter of fact, it's preferred over a decimal. Let's get to some practice. So how would I solve this using the square root property we just mentioned? Well, I want to just, instead of subtracting 169 and trying to find the perfect difference of perfect squares, I'm just going to do the square root of both sides. Square root of x squared gives me x, and the square root of 169 gives me plus or minus 13, because 13 squared is 169. What is that saying? That's simply saying that x is going to equal negative 13 and x is going to equal positive 13. So those would be my two solutions here. What about this one? Well, this is not in the right format that I want to use for this procedure. So I'm going to have to add 48 on both sides in order to make it so. So I would do x squared and 48 because I need this to be all by itself with a coefficient of 1 in order for me to work this correctly. So now I can do the square root on both sides. That gives us square root of 48 is plus or minus the square root of 48. Now, though you may be tempted to stop there, don't, because now, as we've talked about in the previous lesson, this is not in simplified form because there are perfect squares that are factors of 48. What do I mean? What I mean is that if I made a factor tree and I thought about the things that I can multiply to get 48, there are some perfect factors in here. I'm trying to think of 16 times 3. For instance, will give me 48. Why 16? Because 16 is a perfect square. 4 times 4 gives me 16. Well, that's important because now when I write this, instead of square root of 4, I'm going to write plus or minus. Square root of 16 is going to be 4, and this is going to stay square root of 3. So those are my two answers, plus or minus is 4 square root of 3. So I can write it 4 square root of 3 and negative 4 square root of 3. What was that? Negative 4 square root of 3. Let me say x equals and x equals. Here you go. There are your two answers that you want to get for this one. And so go back to a previous lesson about how to simplify those if needing help. All right, so as I mentioned just a second ago, we need this to have a 1 as a coefficient in order to apply the square root property. So there's a 5 here. How can I get rid of that 5? Well, this is being multiplied to there, so I do the opposite. I do the inverse, right? I'm going to divide by 5. And by dividing by 5, I now get m squared. 80 divided by 5 gives me 16, I believe. So this is going to be 16. And now I can apply my property that says the square root of both sides because I want to know m, not m squared. So now by doing square root, I get m. And the square root of 16 is plus or minus the square root of 16. I don't want to forget that because that's a big one I forget. So it's going to be two answers. M equals 16 and m equals negative 16. Why? Because I can put 16 squared here, or I can put negative 16 squared, because negative times a negative gives me back that same positive. All right, so I mentioned to you in the rule earlier, and I kind of did it in passing, that k had to be greater than 0. What do you mean k? The number that was here after the equal sign had to be greater than 0. But what if it's not? What if we have a k that's less than 0? What happens? So let's explore what happens by looking at this problem. So I need to get this q squared by itself, so I'm going to subtract 24. And doing so gives me q squared equals negative 24. Well, now I need to take the square root, right, of both sides. So I take the square root of both sides. And the square root of q squared is q. And the square root over here is plus or minus the square root of negative 24. Now we have a problem. What's the problem? Because I need a number inside here that can multiply by itself to give me that answer. Remember? So let's take 9 for instance. So square root of 9 is equal to 3. So what does that mean? That means that if I had a square, 3 and 3 will be my sides that give me an area of 9. But what if that 9 was negative? Now how would I get it? Well, what times what would give me a negative number? Well, as you can think about it, you're probably having a hard time because you want to say negative 3 and 3, but the numbers have to be the same for a square. You want to say negative 3 and negative 3, but you know better than that because negative times a negative is a positive and I need a negative 9. In other words, it won't work. I just wanted to explore that with you because that's why in the beginning we said k had to be greater than 0 for this to work, because you can't take the square root of a negative number. At least not now. Later on in your math journey, you'll discover something called imaginary numbers that allows us to do this, but you don't have to worry about that now. So we're going to move on. All right, so remember we first isolate the quadratic term and then make the coefficient equal to 1. So we need to get this u squared by itself, and we have all this other stuff over here that needs to go. So let's go ahead and isolate that. We're going to subtract 5 like we normally would do when isolating any other variable. That leaves us with 2/3 u squared equals 12. Is that 12? Yeah. And now we have 2/3 u, so we need to divide by 2/3, or in other words, multiply by 3/2. So dividing by 2/3 is going to be the same thing as multiplying by 3/2. I prefer to multiply by 3/2. So these are going to cancel out right here to become 1. So now I have u squared equals 12 times 3/2, which is the same thing as 12 divided by 2, which is 6. 6 times 3 is 18. So here's my problem. Now I got it back to the form I'm comfortable with. I don't like that u that I just drew. So let's erase that. There we go. So how do I do this? So we're going to continue to do the same thing to get rid of that square. We're going to square root. And square root of u squared is u. Not me, but u. Square root of 18 is plus or minus the square root of 18. Well, are we done? We got both answers, square root of 18. Well, I know that there is a perfect square under that 18. So what is it? 9. So I know that square root of 18 can be broken down into a square root of 9 times the square root of 2, because 9 times 2 is 18. Why was that important? Because this perfect square needed to come out of that radical. So now my answer is actually u is equal to 9 square root of 2 and negative 9 square root of 2. And those are your two answers. There we go. All right, the solutions to some equations may have fractions inside the radicals. What do you do when you have a fraction underneath a radical? So when this happened, we have, a fraction as a denominator. We have to rationalize the denominator. So let's see what I'm talking about here. Plus 4 plus 4. And that leaves us 2c squared equals 49. I'm going to divide by 2 to get this c squared by itself. That leaves me c squared equals 49 over 2. Oh no, what did I just do? 49 divide, yeah, 49. Did I divide that already? Yes. Okay. We already have 49 over 2. I was going too quickly. All right, so I have this situation here. Now I need to take the square root of both sides, right? Square root of this and the square root of all of that. How do you handle the square root of 49 over 2? What do you do for a fraction? Well, fortunately, it's pretty simple. Oh, you know what? I forgot my plus or minus. Don't want to forget that. It's really simple. That's the same thing as saying the square root of 49 over the square root of 2. So you just find the radical, simplify the radical for the numerator and the denominator. So square root of 49 is going to give me 7, and square root of 2 is just going to be square root of 2. Nothing I can do there. So this is still plus or minus. I don't want to forget that because I'm going to have 2 answers. Now, what we're talking about here is, as far as rationalizing the denominator, is that it is not proper to have a radical in the denominator. So in order to deal with that, here's what we'll do. We're going to multiply 7 square root of 2. We're going to multiply this fraction by 1. But not just 1. We're going to make that 1 square root of 2 over square root of 2. So basically, we're going to take whatever's in that denominator and multiply it by 1 by making itself above itself. So square root of 2 on square root of 2. What is square root of 2 over square root of 2? Well, that's just 1. Anything divided by itself is 1, but it allows us to get rid of this square root on the bottom. How? Because 7 times square root of 2 is 7 square root of 2, and square root of 2 times square root of 2 is just 2. See, notice now I no longer have that on the bottom. So my answer is 7 square root of 2. At least that's one of my answers. What's the other one? Minus or negative 7 square root of 2 over 2. So those are my 2 answers here for this problem. So I wanted you to see, because you're definitely going to see that happen sometimes. So I want you to be comfortable with that. All right, what if you have the parentheses? What if this whole thing is being squared? How do you handle it? Well, fortunately, we're going to handle it the same exact way we handled it when it was just a variable, an x or a u. We're going to take the square root of this whole piece and the square root of this whole piece. So that leaves me, the square goes away. Now I just have x minus 3 left. And I'm going to have 16. I want to say plus or minus 16. So I have a plus or minus 16. So that means I'm going to have an x minus 3 equal to 16 and an x minus 3 equal to negative 16. So I have 2 solutions here. I'm going to add 3, and x is going to give me 19 for 1, and add, oh, you know what? I said, yeah, I did good. So plus 3, so x equals negative 13. So those are 2 solutions that we're going to get there. So we're going to do the same thing here. I want you to pause it and you work this one first before I do so. And sometimes I forget to tell you to do that, so please get in the habit of doing so. Pause it every time you see me come to a question to work it on your own. You'll learn it faster that way. All right, so I'm going to do this side the same way. I'm going to take the square root and the square root. And when I do that, the squared is taken care of. y minus 7 equals the square root of 12. Well, what's the square root of 12? The square root is going to be plus or minus the square root of 12. Square root of 12. And so I have 2, that looks like this. So I have 2 ways, 2 solutions here. Y minus 7 equals square root of 12, and y minus 7 equals to negative square root of 12. And it's okay that the negative's on the outside of that radical, but it can't be on the inside. It can be square root of negative 12. So this is okay. So we're going to add 7 to both sides here. That leaves me with y equals 7 plus the square root of 12, because I can't add the 7 to that 12 on the inside. We just have to leave it this way. And when I add 7 over here, it's going to be the same way. Add 7 here. It's going to be y equals 7 minus square root of 12. So those would be your 2 answers there. All right, remember when we take the square root of a fraction, we can take the square root of the numerator and the denominator separately, which is what we've done already. But let's look at this again with these 2 fractions. Wow, this is like a lot going on in this problem. But when you know that you can square root this whole square, it makes it so much simpler. So I'm square rooting both sides there. This leaves me with just x minus 1/2 equals, so what is this the same thing as? Well, the square root of 5/4 is the same thing as square root of 5 over the square root of 4. Well, what is the square root of 5 and square root of 4? That leaves me this plus or minus, don't want to forget that, square root of 5. The square root of 4 is just 2. So I'm left with just that. Now I have two problems to work. I have x minus 1/2 equals square root of 5 over 2. And I have x minus 1/2 equals negative square root of 5 over 2. So how would I work that? The same way as usual. We're going to add your 1/2 on both sides, leaving you x equals the square root of 5 over 2 plus 1/2. And that's going to give you, well, the denominators are the same, so I can now add this. This is going to give me 1 plus square root of 5 over 2. Notice I put the 1 in front, and you don't have to, but it's usually the algebraic etiquette is what I call it. It's just the proper way we usually write it, but both ways are fine. So we can now put it all over 2, and we can also write this as plus 1/2, plus 1/2, plus 1/2 on both sides. So this goes away. X now equals negative 5 square root of 5 over 2 plus 1/2. And as we've seen just a second ago, those are going to come together to get 1, and this time it's minus square root of 5. So this is what we get. So those are our two solutions for this problem. All right, so we'll start the solution to the next examples by isolating this binomial. So this added one more step, which is needing this binomial to be isolated. So we're going to subtract 3 to do that for this problem. And now we're left with our x minus 2 squared equals 27. Now I can do my square root, because whenever you have everything over here being squared, you can now use your square root. And you want to do that on both sides, because whatever you do on one side, you do on the other side. So this leaves me with x minus 2 and the square root of 27. But it's going to be plus or minus the square root of 27. So there's my two problems. Square root of 27, I know there's a perfect square in there. So square root of 9 and times the square root of 3. So that leaves me 3 square root of 3. So I just wanted to go ahead and get that out the way. So now when I'm solving this, it's going to be x, well, when I add my 2, let me go ahead and do that without breaking it into two problems. When I add my 2, it's going to be x is equal to 3, let's do 2 first, 2 plus 3 square root of 3. And when we add 2 on the other one, it's going to be x equals 2 minus 3 square root of 3. So those are our two solutions for that one. Might you work this one on your own? See what you get. See if you come up with the same answer. Pause it here and work this one. So this one's already in a format where I can take the square root. So I'm going to take advantage of that. So if I take the square root of here and take the square root of here, then I can go ahead and start working. 3v minus 7, square root of negative, can't do that. Can't do the square root of a negative. So this one's already going to cause problems. So this is not going to render a solution, because there's no number, there's no way I can get a square root of a negative term. So this one's not going to be able to be solved at this point at all. So we're going to have to stop there for that one. All right, the left sides of the equation in the next two examples don't seem to be in this form, but they are perfect squares. So remember, we talked about perfect squares. We can actually put it in that form. So we'll factor them to put in that form. So for this one, I recognize that this is a perfect square. This last term is a perfect square. And when you multiply those square roots by 2, you get this middle term. What am I saying? I'm saying that if my a, because you remember our form is a squared minus 2ab plus b squared. So I see this set up here. So if my a was equal to p, making that p squared, and my b was 25, then I could just multiply these two together. 5 times p is 5p times 2 is 10p. So I know this is a perfect square. So I could actually break this into a perfect square that says this is going to be equal to a minus b squared. So I'm going to write, instead of a, I'm going to put p there. So this is going to be the same thing as saying p minus 5 squared is equal to 18. So now I've did that one step. It makes it so much simpler for me to do the square root. So I can take the square root of this side and the square root of here and get p minus 5 equals the square root of 18. Well, the square root of 18 has a perfect square in it because it has a 9. So the square root of 9 is 3, so that's 3 square root of 2. So I know this is going to be plus or minus this 3 square root of 2 when I take the square root of 18. So that leaves me 2 answers again. So it's going to be, when I add 5 here, the 5 is going to be in front to be, actually I could just write this simply. I don't know why I didn't think about that. I could just write 5 plus or minus 3 square root of 2. Man, that's so much better. And that's the way you're more likely going to see it. So 5 plus or minus the square root of 3. So these are 2 different answers, right? 5 plus 3 square root of 3 and 5 minus 3 square root of 3. All right, same thing here. I have a perfect square. I can see that because this is going to be 2n and this is just 1. And I remember my formula that says a squared plus 2ab. And this is on your reference sheet for your STAR test, unless they changed it, but it's always there at the top. This is the same thing as saying a plus b squared. So I can see that I have a perfect square here. That's going to be a 1 because 1 times 1 is 1. And when I break it down, I could take this 2n plus 1 and square it off. And that's going to be equal to 16. So I changed nothing here. I just factored it so it can look easier for me to do this square root property. Take the square root of both sides and it gets rid of this square, leaving me 2n plus 1 equals 4. But that's plus or minus 4, and that's a real number, so I can add it to whatever I'm about to do now. So that's pretty nice. Subtract 1. Actually, let me break this into 2 problems before this looks too messy. So let's get hot pink. And we'll break this into 2n plus 1 is equal to 4, and 2n plus 1 is equal to negative 4. Now it's going to be a lot easier to just work it like we do any other problem. 2n equals 3 divided by 2, n is equal to 3/2. Double check that. Yep, looks good. So we're going to subtract 1 here, and that leaves us 2n equals negative 5 divided by 2, and we end up with n equals negative 5/2. There we go. All right, so that's how you would handle that if you had a perfect square situation. Time to look at what is it going to look like on the STAR test. So here's the equation. A few years back, the function L is equal to 0.8 t squared models the relationship between L, the length in feet of a pendulum, and t, the period in seconds of the pendulum. You know the pendulum, like this I don't know how to, it's like something swinging back and forth, like pendulum. All right, so which value is the closest to the period in seconds for a pendulum that is 30 feet long? So we're going to replace our length for 30. So we're going to say this is 30, and I'm going to write it in a similar format that we've just gotten used to, so you can see that it's the same type of work. So I'm going to say 0.8. Actually, you know what? Before I do this, let's pull out the calculator, because we're on a test now, and I want to use all my resources. So I'm going to pull out the calculator to work this one. All right, so now let's set it up. 0.8 t squared equals, we already know that length is going to be 30 feet. So look, it's almost what we've talked about with the square root property if we get this t with a 1 in front of it. So I'm going to divide 0.8 on both sides to get that 0.8, and then I'll use my calculator to figure out what is, let's go to calculator, what is 30 divided by 0.8. You could just put 0.8, but that's 0.08, 0.8, and I get 37.5. So now I know that t squared equals 37.5. So to find this, I need to do the square root. See, look at that. It came back up even on the test. And my answer is going to be equal to t equals plus or minus the square root of 37.5. Now, what is t representing anyway? T is representing some period in seconds. So we got to remember that's time, because we're thinking in real life now. And you see that they actually do want a decimal for this one because we're talking about a real life situation in seconds. So I'm already going to think, if a negative seconds doesn't make sense. We're not going to say -3 seconds passed, but positive seconds make sense. So I'm probably not even going to give any credence to a negative answer. So I'm going to go ahead and use my calculator to do square root of 37.5 and see what we get. So we get 6.12 seconds. So the closest to that is J. Bam. A lot of people miss that one, but you won't anymore because you know how to set this up using the square root property. Another problem was like this one. So to get this x squared by itself, we could do the same thing like we did a second ago. It's one more step on this one. So I'm gonna rewrite this so you can see what I'm talking about. I'm gonna get this x squared by itself. I'm gonna subtract 72. And that leaves me -4.5 x squared equals -72. And I'm going to divide by -4.5. -4.5. And whatever I get is going to leave me with my x squared. So that's what I want to do, get my x squared by itself. So there's many ways, by the way, to work this. But using this property is one of the ways that you can use. So we're going to take my calculator and do the work. There, 72. Divided by 4.5. Nope. 4.5. Yes, I do know that they're negatives. So I know that negative times negative divided by negative is a positive. So it doesn't matter that I leave both of them positive. And that's going to give me 16. Oh, that looks beautiful now. So the square root of x squared equals 6. So this is going to give me, when I take the square root of both sides, this is going to give me x equals plus or minus 4, right? So that's my solution. So if we were dealing with a real world problem, I'll start thinking about that plus or minus differently, but this is just an equation. So now here's the question. The equation has x equals 4 as its only solution. Nope, that's not the only solution. The equation has no real solutions. No, it has some solutions. The equation has x equals 4 and x equals -4 as its only solutions. Yep, the equation has infinite. Nope. So H is our only reasonable choice there. And that brings us to this one here. We just did that one actually. This sets up the same way, so I'm not going to do that one. Did we answer our question? Yes, solve quadratic equations having real solutions by taking the square roots. We solved them by taking the square roots. Good job to you, fantastic. And we kept them in this form, right? Ax squared equals some number, or we have parentheses where we divided that number and then did the square root. So great job to you. My name is Brandon Clayton, the Algebra Guy, and I will see you next lesson.